Good evening. I'm Lee. I'm going to give a report on the WIMP search with CDEX and TEXONO experiment. First, I will explain the CDEX and TEXONO experiment, and then I will show some results based on the spin-independent chi-n scattering with the Earth scattering correction. And then I will show some preliminary results on the chi-e scattering. So basically, the direct WIMP search is looking for two ingredients, which is a time integral and the annual modulation. The time integral is looking at the excess count in the time integral spectrum. The problem for this is that it needs some background modeling. And the other is that looking at the annual modulation effect due to the Earth rotation relative to the rest frame of the galaxy. So first, we were looking at the chi-n interaction, and basically this consists of three types of the interaction related to this chi-n interaction. The first is the normal chi-n interaction, which we are looking at the cost energy of the nuclear, but there is a limitation on the minimum value of the WIMP mass that we can prove due to the kinematic bound. The other is that the so-called middle effect. When a nuclear is recoiled, it will bring the whole electron cloud with it, but there is a small chance that one of the electrons will left behind and causing a excited state, and this will give us a larger larger deposit energy. And the other effect which we are trying to look at is this the brainstorm. However, the count rate for this effect is too low. It is unobserved. It cannot be observed in the underground lab due to the Earth scattering. The CDEX experiment is located at the Hau-Bin underground lab in Sichuan province in China. The lab is located at in the middle of the 17 kilometers tunnel, and which this is the deepest underground lab in terms of muon flux and in terms of rock overburden. So this is the interior view of the lab, and the CDEX-1B experiment is sitting inside this lab shooting, and this is the interior view of the shooting. And in the run one, the 1 kilo point contact germanium detector is covered by a sodium iodide detector, and in the run two, the sodium iodide detector is replaced with some copper. And here we adopt a 160 eV threshold for a time integral analysis, but due to the fluctuation of the noise edge, we adopt 250 eV for annual modulation analysis. So, and for the TEXONO experiment, this is the experiment located at Taiwan and in the power plant, and the detector is 28 meters from the nearest one of the core. And showing here is the shooting configuration. At the outer layer is the plastic scintillator, and there's lead, there's copper, and this is how the detector look like. It is also covered by a sodium iodide detector. The data we show in this report is of 500 gram with 60 days of data taking. The threshold is 200 eV. So showing here is the CDEX 1B data, the lowest 3 energy bin, and you can see that this is consistent with no hypothesis. We didn't see any modulation signal here. And showing here is the time integral spectrum, and this is when we fit a modulation function at the previous plot, then we get this black dot. It is consistent with no hypothesis. So one thing we will like to consider is the Earth in this analysis is the Earth scattering. The reason is that when we are looking at the middle effect, the sensitivity is usually is located at the 10 to the minus 30 centimeters square of the cross section. And in this cross section level, actually part of the dark matter will be blocked by the shielding and the Earth itself. For example, showing here is at 10 to the minus 38 centimeters square. The Earth is almost transparent for the dark matter. However, if we go to a higher cross section, for example, 10 to the minus 27, then the Earth is no more transparent. It will block a lot of the dark matter. So when we draw the exclusion plot, we need to take this into account for the middle effect. Showing here is how the velocity spectrum change due to the at different cross section. You can see that at the low cross section, part of the velocity will go to 0. And if the cross section go higher, then part of them will go to 0. And then if the cross section go even higher, then almost all of the dark matter will accumulate at the lowest speed. And showing in the last row is the difference of the Lecoq spectrum before and after this scattering effect. You can see when the cross section go higher, we will measure less and less event, and then at the end we will not measure anything if the cross section is too high. So we can visualize the concept into this plot. So the black line at the middle, which is the x equal to y line, is if all this is transparency, and then we will measure the sensitivity and the real sigma, the real cross section and the sensitivity cross section will be the same. But at when the real cross section is too big, actually the sensitivity will drop, which means we cannot measure anything above this sensitivity. So showing here is that the red curve is the CDEX at the CDEX, and the blue curve is as the TAUP experiment, which is at the surface. So it will allow more dark matter, and it will probe more the higher cross section here, which is unable to be probed by the CDEX. So showing here is that this is why the brainstorm, because of this sensitivity, so the brainstorm cannot be observed at the underground lab. So this is the result. So this enclosing is from the CDEX, and this part is from the middle effect. This part is from the normal chi-n scattering. And what is worth mentioning that due to the surface location of the TAUP experiment, it can able to probe this higher cross-section region, especially in this region which is unprobed by other experiment yet. So Another interesting topic is this the Chi-E scattering. And this Chi-E scattering is parameterized by two effects, which is a short range and WIMP and the long range. And this is based on the multi-body atomic calculation. The theoretical calculation is from this paper. So you can see there's some structure here, which is from the German atomic effect for both long range and short range here. So this is a preliminary result from the Chi-E scattering, and we are not only doing the calculation for the CDEX and TEXONO data, we also do this Chi-E scattering calculation for other experiments as well. And to complete the fitting, we are using a 3-component fitting, which is the Chi-N and the Chi-E short range and the Chi-E long range fitting, and fit this all component together. And showing here is, you can see there is a closed loop from Dama here for the long range and short range. But bear in mind, one important is that although it seems that the Dama is consistent with 0 here, actually this is not consistent with 0. The reason is that the short range and the long range is highly correlated. And this showing here is the modulation amplitude from the Dama, and giving this this is showing this curve is the Chi-N plus Chi-E best fit. So the summary. So we have updated our previous Chi-N result with the Earth scattering correction, and we have this CDEX give a best result down to at 0.06 GeV, and also there's a small region at the low mass, which can only be excluded by the TAUP experiment. And also we do a Chi-N plus Chi-E global fit for CDEX and various experiments. And the next plan will be that with the Chi-N and Chi-E do the exclusion plot with the Earth scattering effect. So thank you, that's all.